Hello. So we were working on a graphing problem and we started to graph this function f of x equals to e to the x times sine x. In the last video, if you have not watched it, you should. We computed the first derivative, and not only that, we converted this first derivative into this particular form, which is more useful for our purpose. And then we found the critical points where the first derivative is 0. It's never undefined because exponential and sine function are defined on the entire real line. And then we plotted these critical points on the number line for f prime x. So basically we have a straight line which is a model for real number system, and then on that number line we plotted the critical points which are in blue, and let me put the endpoints in red just to differentiate them from the critical points. So basically we have these 6 values which we need to worry about, and we will see how we will manipulate this or use this number line to extract more information about the behavior of this function. But before we do that, let's compute the second derivative, which is easy to compute from this particular expression, the first expression. Let me do it just here. It will not take much space. F prime x is e to the x sine x plus e to the x cosine x. So f double prime x is just e to the x sine x plus e to the x cosine x. Okay, minus e to the x sine x plus e to the x cosine x. So that means we can cancel off something. These two we can cancel off. So we have got 2 times e to the x cosine x. So it's basically product rule. It's quite simple. And we record this information in this slot. By the way, if you have not downloaded this slot, this particular template that we have created for this type of problems, you can do it from the description of this video in YouTube or in our website cheenta.com, where we have uploaded a copy of this. All right. So we have the second derivative. Now we want to find out the second degree critical points. That's the points where the second derivative is 0 or undefined. So we set these second derivative equal to 0. Let's do that. Let's set the second derivative equal to 0. So 2 times e to the x cosine x. That's my second derivative. Let's set that equal to 0. Obviously 2 times e to the x is never 0 because exponential function is always a positive function. So this is 0 only when cosine of x is 0. Let me write that. In fact, second derivative is 0 only if cosine of x is 0. So clearly cosine of x is 0 when x is some odd multiple of pi by 2. And this happens for obviously infinitely many times, but we are interested only between negative 2 pi to positive 2 pi. That's what the problem says. Let me go back to the problem and show you that. The problem actually wants us to focus on this particular interval from negative 2 pi to positive 2 pi. So let's do that. Let's find out for what value of k x is between negative 2 pi and positive 2 pi. So we can easily divide by pi and we get negative 2 less than equals to 2k plus 1 by 2 less than equals to 2. So basically negative 2 minus half is less than equals to k less than equals to 2 minus half. So in this case we get k equals to negative 2, negative 1, 0 and 1. Realize k is an integer, right? So we are only worried about the integer values of k. Now this gives us a description of what the value of x is. So when k is equals to negative 2, so k is equals to negative 2, x is equals to negative 3 pi by 2. X is equals to negative 1, k is equals to negative 1, then x is equals to negative pi by 2, x is equals to 0, k is equals to 0, which means x is equals to pi over 2, and we have finally k equals to 1, which gives us x is equals to 3 pi by 2. So we really have these four values between negative 2 pi and positive 2 pi. So let's record that in this chart. Negative 3 pi by 2, negative pi by 2, positive pi by 2, positive 3 pi by 2. So we have these four values which are called second degree critical points when the second derivative is either undefined or it is 0. We will plot them on the number line. So let me plot the endpoints in red and all other points, the actual critical points, second degree critical points, as in blue. So there is a difference in the picture. So we have a bunch of information available to us now. Next, we want to compute the maxima minima. The maxima minima are basically the critical points about which the sign of the first derivative changes. So, and then we want to also find the inflection point. The inflection point. It's the second degree critical point about which the sign of the second derivative changes.